research. We all know that haze is an important factor for the usability of remote sensing imaging. That means if haze can be removed from the imaging, maybe the image can be more useful and in your application. Traditionally, there are several methods for haze removal. The first one is so-called dark object subtraction, and another one is haze optimized transformation. The objective of this method is to find the difficulty in above-mentioned method and find some solution to improve above-mentioned method in haze removal. For dark object subtraction, actually is, for example, actually is use those pixels with zero reflectance. If those pixels with zero reflectance has radiance in your image, then those radiance must come from the haze. So we can use those radiance from zero refractive object as a reference, and we remove those amount of radiance from your image, and then the haze can be removed from your original image. But we know that this method is based on the assumption that the haze distribution is homogeneous in the whole of your images, but usually that is not in this case. So there's another method called haze optimized transformation. Usually, actually, in this method, we have to find a clear vector from your image. That means we have to collect those pixels without haze contamination from your source image, and then we measure, and from this image, we can see for a certain classes the trajectory of the haze. I mean, for some certain classes, when the haze is increases, the trajectory will move like this one. Because the radius for haze is different for different wavelengths. Usually, the shorter wavelengths will emit higher radiance. So, for example, this is a situation from let's say TM image. TM1 and TM3. TM1 usually is in shorter wavelength, so it observes in this band. The TM1 emit more radiance than TM3. So the trajectory of some classes will be the haze trajectory of some certain category will move as this one, because the radiance in TM1 increase fast more higher or larger than TM3. So in this method, haze optimized transformation. In this method, they define a vector called in this direction to measure the thickness of the haze condition, and then from this estimation, it can derive a correction for the haze situation. So in here, for a certain amount of haze, we can have, for example, the hard value will be in this line. Because in this case, the distance here is the same. For the image object in this line, that means they suffer from the same haze condition. So if we take the minimum pixel value here, that you can see, you can regard this point is the in this haze condition, the minimum. This is equivalent dark object in this haze condition. So once we can remove the gray value from here to here, from here to here, then we can say the haze can be removed. And usually we call the value in here is a G minimum hot. That means the equivalent dark object gray value in this hot condition or the haze condition. But in real case, this is two image with cover same ground location. This one is Landsat ETM image, and this one is Formosa satellite image. We know that for Landsat image, the spatial resolution is 30 meters, and this one is 8 meters. And this is a scatter plot of this image, and this is a scatter plot of this Formosa satellite image. You can see that in this scatter plot, because its resolution is higher, so it can see more detail for object. So it's spread larger area than say images. The ground cover, the ground object is almost the same because you can see the date of the image creation is almost the same. But you can see the scatter plot of Formosa image spread larger areas. So once this image has haze contamination, and you can see, okay, yeah, for example, if there is haze over here, so you can see there should have the scatter plot of this image should be like this, because some of pixels is affected by haze, and their position in scatter plot should be over in this area, and this is the same situation for Formosa satellite image. But okay, so for some specific haze condition, its hard value should be over this location. But for higher resolution image, the equivalent dark object value will be located here because it will affect by its original, some detailed ground object, because you can see in its original scatter, it spread larger areas. So it is very possible to give you a wrong, the dark object, equivalent dark object estimation value. So that means you will have wrong correction for your haze image. So in this case, we have find some way to modify the original method and make it suitable for high resolution images. So first, so we have to do some modifications. But when we look this term, the equivalent dark object value. In this value, it should be a monotonic increasing function because the higher haze condition, this correction must be higher. But in later figure, you will see that is not always correct for original source image. So we have to make some modification. This is the case. The black line, the dashed black line here means the original equivalent dark object gray value we calculate from the source image. But you can see that this is not a monotonic increasing image. In some position or in some specific hard value will looks very strange. So so we make a modification like this blue line. We ignore those irregular variation. We make it a monotonic increasing function. But you can see that the blue line here is almost a step function, not haze effect from nature phenomenon. So we have to do some smoothing from this blue line. Actually, here we use smooth. Here we use some smoothing method to smooth the original blue line to make it more smooth. So right now, the equivalent dark object for different hot condition or a haze condition is the red line. Okay. So the last one is the experiment result or test data. Here we use two sample data to test this algorithm. First is Formosa satellite image. You can see in this image the haze condition is different. It's distributed. Different in different area. Then here is more hazy than this place. And another one, even higher resolution image. The resolution is even higher. Here is less hazy area, and here is a very hazy. And so here we okay. So the first we make modification of equivalent dark object, and then we take a smoothing filter to smooth the hard value spatially. Because originally, if the hard image is not smooth, it will show some detailed brown object. It obviously not come from the haze, and it is come from the brown object. So we use a medium filter to smooth this image. But the problem is the window size of the medium filter still not determined. Because if you use too small, too small size of, the medium filter with a small window size, there are some paper and soil noise in the result. But if your smoothing filter is too large, okay, the variation of haze certainly may be smoothed out, and then you cannot get haze remove the image, because some haze variation is also smoothed. So here we use a method called here we measure the variation of high frequency variation, because usually haze is a low frequency variation in your images. Suppose in your method you cannot change the high frequency response of your image, because your haze is in low frequency variation. So in this case, we use FFT and the high pass filter to get a high frequency information of your source image and your haze removed image. If your window size is not suitable, then your high frequency response will be affected. So in this case, we can try to select a window size that is not affect the information over here. By high frequency part, then you can get a suitable result. Okay, let's ignore this one. So if this is a source image and this is a hard image before filtering, and if you have a suitable window size, then you can get a more suitable, a good hard image result. And this is a noise we measured from the haze removed image. In this chart, 100% means there's a lot of noise in your high frequency part. So once your noise in your high frequency part is very low, it's not changed. The same as your original one. Then maybe this one is a good result for haze removal, a good result from haze removal. So this is here is the original image, and here is the haze removed result. In this case, for one image, we see that 9 by 9 window size is more suitable, but for ICRS, it should be increased to 17 by 17 window size. And then you can see, if you use different smoothing window, you can see in this one is not, is the result without any smooth, so you can see a lot of noise you see. But if you use a suitable window size here, you can see the result may be more reasonable. And here is the case of ICRS. You can see if you use suitable window size, the result may be should be better than without the wrong window size. So in conclusion, we can in this method we can have modification for hard algorithm and get better result in high resolution image. And okay, by our method we can provide better result for one set and ICRS maybe. That means maybe we can use methods for other high resolution images.
Thank you, Mr. And again, we welcome your question. Do you have any question? And very thank you for your joint attention and your discussion. Now we have a break time.